Hey everypony, hope you all having a good time out there. Today we're going to talk about how to graph polar functions a little bit differently than what you did last year in pre-cal. So you might remember last year in pre-cal you would graph a function like this, a polar function, r equals 2 sine theta. I know it's polar because polars, remember, have to be in terms of r and theta. Now last year when you graph this, you should first recognize that this is a circle. You would have to graph a whole bunch of points, theta and r, right? You pick a theta, you start with 0, go pi over 6, pi over 4, pi over 3, pi over 2, and all of them. And it took forever to graph those. Well, we're not going to do that anymore. We are going to only use the quadrantals. And what do I mean by that? We are only going to use the main cornered. And the reason we like the quadrantals is because they are, when we deal with sine and cosine, they are always either going to be zeros or ones. There we go. 0 or 1. And that makes everything just a little bit easier for us to do. So let's see here. If I plug in 0, pi over 2, pi, 3 pi over 2, and my favorite mathematical wrapper, 2 pi. So when I graph this circle with a radius of 0, if I theta is 0, I plug it in, sine of 0 is 0, so that's going to give us 0. Plug in pi over 2, sine of pi over 2 is 1, that gives me a radius of 2. If I plug in pi, I'm at 0, and if I plug 3 pi over 2 in, sine of 3 pi over 2 is negative 1, so this gives us a negative 2. Now that's very important for us. We'll talk about that. Plug in 2 pi, back to 0. Alright, looks like when I grade some papers, 0, 2, 0, 2, negative 2. That's bad. Alright, so when I graph this, remember how to graph polars. I'm facing 0 radians, and I go out 0 units. So there I am. Now next, I'm at pi over 2. At pi over 2, I step out, come on, stop doing that. I step out 2 units. So what happens in between? Now hopefully from pre-cal, this is where your pre-cal is going to have to help you. We actually have a curve. It's going out like this. There we go. Now, at pi, I'm back to 0. So that means between pi over 2 and 0, take a look here, between 0 and pi, I know that my radius is greater than 0 because I'm going from 0 to 2. Same thing. Between pi over 2 and pi, I also know that my radius is greater than 0 because I'm going from 2 to 0. So I know that my radius starts off at 2 at pi over 2 and ends up at 0. So I can just go ahead and do that. It's going to be curvilicious. Now notice, this is one complete circle. That's all we need. So the radius for something like this, the domain here is always going to be 0 to pi. Okay? The domain is. Okay? So always 0 to pi. This is one complete circle. Now what would happen if you continued though? Well, now I'm facing pi and I'm going to 3 pi over 2. So what does that mean? I'm facing 3 pi over 2, but I go backwards. I'm just going to overlap. So this is all an overlap. And therefore, we don't want it. Don't need. So I'm going to scratch those out. Okay? This is all we want. So if we have r equals some a cosine theta, or r equals a sine theta, theta is always going to be between 0 and pi. Right there. So what about some other ones? Well, let's take a look at a lemmason. A lemicon, if you're French, okay? Let's take a look at, let's say, 3, I don't know why I keep doing that today, 3 minus 2 cosine theta. Same thing. When I graph this, theta and r, whoop, that should be an r, old habits die hard. If I plug in a theta, 0, pi over 2, pi, 3 pi over 2, and my favorite mathematical wrapper, 2 pi. Let's plug these in. We get cosine of 0, which is 1, so this becomes 1 pi over 2 is 0, so that becomes 3. Plug in pi, that becomes negative 1, so we get 5. Plug 3 pi over 2 and 0, back to 3. Plug in 2 pi, that's going to get me back here. Now notice, I didn't start repeating until here. That's very important for us, okay? So when I graph this, remember, I only want the quadrantals. 0, pi over 2, pi, 3 pi over 2, and 2 pi. So let's graph it. When I'm facing 0 radians, I go out 1 unit. 1 unit. At pi over 2, I go up to 3. At pi, I'm facing pi, I go out 5 units. At 3 pi over 2, I go out 3 units. And then I'm back to 1. Now remember, in between, my radius is increasing. Between 1 and 3, it's decreasing. But I'm not going to go like a line. That'd be boring. Remember, it's curvilicious, so it's going to go out. And keep going. I'm going to make a sweeping. And as I'm sweeping, I'm making like these little curves. Goes to 3, and then we get a lemison. I can't remember the rule if it's dimpled or not, but there's your basic shape. There is your lemicon right there. And we can do this even with a looped lemison. Ready? Let's take a look. R equals, what if I did 2 minus 4 sine theta? Something like this. Well, if I graph my quadrantals, theta and r, 0, pi over 2, pi, 3 pi over 2, and 2 pi. My favorite mathematical wrapper. Plug in 0. Well, sine of 0 is 0. 2 minus 4, 2 minus 0 is just 2, sorry. Pi over 2 gives me 1. We get negative 2. Ooh, that's important. We'll talk about that in a second. Notice we go from a positive to a negative. Ooh. All right, we'll talk about that. Plug in pi, back to 0. 3 pi over 2 gives me negative, and that gives me 6. And 2 pi gives me 0 and back to 2. Is that all good? All right. So let's go. Ready? Draw my coordinate system. 0, pi over 2, pi, 3 pi over 2, and 2 pi. So let's graph it. When I'm facing 0, I'm out. Keeps doing that. I go out 2 units. At pi over 2, take a look. We are at negative 2. So I'm facing pi over 2, but I'm going to negative 2. Right there. Now we'll talk about what that means. So let's talk about this. Now notice, between 0 and pi over 2, I'm measuring my angle, remember, going this way. So what is this telling me? I am sweeping up, but at some point the radius must equal 0. So we can say on the domain 0 to pi over 2, the radius has to equal 0. If that sounds familiar to you, it should. So between 0, as I'm sweeping out, and at pi over 2, I have to hit a radius of 0. In other words, we'll go through the pole. So it's going to look like this. Now, at pi, I'm at a radius of 2. So between pi over 2 and pi, I have to go back through the pole. Again, so I know that somewhere on the domain, pi over 2 to pi, the radius has to be 0. So it's going to kind of sweep like this. So it's going to cross the pole there. Now, I'm here at 3, and if you notice, it's a vector, right? It's kind of like directions. At 3 pi over 2, my radius is 6. And then we're back to 2. And we get our cardioid. Now, one thing I want you to notice about my cardioid here. Whoops, sorry, this is not my cardioid. That's terrible to me. What do we call this again? This is our looped lemison. You had never corrected me, although there's probably a bunch in the video right now, in the feed right now. That's our looped lemison. But I want to pay attention to is the looped part. We're going to need this later on anyways. How do we find out where the loop is? Well, what's the radius there? At the loop, the radius is 0. So I can set this equal to 0. And I can actually find where those loops occur. We would get sine of theta equals 1/2. And where does theta equal 1/2? Whoops. Well, sine is equal to 1/2 at the following: pi over 3 and 2 pi over 3. And if you notice, pi over 3 is between 0 and pi over 2, and 2 pi over 3 is between pi over 2 and pi. So I know that, so I enter the loop at pi over 3. We exit the loop at 2 pi over 3. And that becomes very important because later on we're going to find what's the area of the loop itself. Pretty cool. All right. Go back to video 2, and we're going to take a look at how we graph flowers, roses.